Namaskar, welcome back. So, this was the last slide where we were talking about that how we resolved the two events from the trench which we dug across the Kutch mainland fault in Kutch, Gujarat. Okay. So, this is how one can do, and mostly we do this type of measurements and try to identify that how many times the layers sedimentary units have moved. Okay. And another example of very detailed mapping, this is again from Kutch, where we have marked each and every fault strand, okay, which we exposed in this. Okay. Now, this is from uh, the Himalaya and the foothill of Himalayas. And the slide here, which I am showing, is to explain that what do you mean by the shear fabric. Okay. Of course, we were talking about in the previous lecture that we traced each and every gravel, and that gave us the fabric of which uh, indicates about the deformation. Okay. And here, what you see that there is a close up of this portion here, the down. Okay. And what we see is the alignment of all platy gravels. Okay. So, in sediment succession, you will also have different shape of gravels, and mostly when there is a movement, okay, then the flat platy shape of the gravels will aligned along the fall plane. Okay. And that is again a very important aspect of identifying the deformation, and that what you see over here. Okay. So, this sandy unit has been dragged along this contact, and you can see there are many gravels which are sitting along this one at the base of the fall plane. Okay. So, this each and every gravel is important for us, which will tell us the pattern of deformation. Another part which we have discussed in the previous lecture also, the amount of slip. Now, sometimes what has been like many researchers, they believe that the amount of deformation, so this is what has been shown as in fault here, this black line over here is your fall plane, and then if there is a movement along this, then possibilities are high that not all units will experience same amount of slip. So, you need to be careful about that also. Okay. So, as you move towards the top or the towards near to the surface, that is ground surface, the displacement may reduces during the same event or the single event. Okay. So, that is another parameter which one has to keep in mind. Okay. Now, identification of litho units is important because based on the identification of litho units or the sedimentary units and the contacts which you have marked, either the depositional or erosional contact, or you are having the tectonic contact or unconformities. Okay. Based on that, you will select the sampling points. Okay. Collection of samples from different litho units, because you need to have the capping of that. Okay. So, what has been shown here is that this QAL2 is displaced, but QAL1 is not. So, this becomes your capping unit. So, age of this is important and age of this is important. Okay. So, you need to have understanding of that before you get into the sampling part. Okay. So, identification of sedimentary units or litho units is important for generating the chronology, geochronology what we say, and those are the ages of that. Okay. So, here what you see is the ages are being shown. So, from where you will collect the samples, and also you can have different methods through which you can date this units. Okay. So, one is what we call the OSL, optically stimulated illumination. We will talk about that in after a couple of lectures, the dating techniques. At IIT Kanpur, we have OSL dating lab, but for C14, that is radiocarbon ages, we either go and submit our samples abroad, or and mostly now we have the facility which has come up at Inter-University Accelerator Center, New Delhi. So we have this facility, and that has been developed under the umbrella of Ministry of Earth Science. So we can now have the ages, radiocarbon ages from IUAC. So mapping of litho units, how we do is that partly I have already discussed that you have to look at the color of the units. That helps you in differentiating whether it is darker units or it is lighter units. So darker units usually indicates that they are older units, provided they are not carbon humus rich. Okay, then you will see that they are very dark, chocolate brown color or something like that. Okay, so that also helps us in identifying or knowing the environment in which they were deposited, and whether after the deposition what environment changes occurred because of the deformation. Okay. Then we come to the grain size. So based on the grain size range, we have right from clay to gravel. We differentiate those units, and then percentage of clast also. Okay, because in some units you will find a scattered occurrence of gravels or pebbles, and in some you will just see the finer deposits. Okay, so you can differentiate and demarcate these units based on this. Okay, then also you can look at the class shape. Okay, whether you are having angular uh, gravels or you are having rounded to sub-rounded gravels. So this all description goes in your interpretation part of the sedimentary units. Okay. Then sorting also, whether they are poorly sorted or well sorted, that you can do. And even if the units are, for example, your gravels. Okay, if the gravel unit, usually most of the time we see that they are the bed load channel deposits. So whether they are matrix supported or class supported. Okay, so whether there was some sort of an event which resulted into the debris flow, or it was just channel fill deposits. Okay, compactness basically, because that what we call the cementation part. Okay, so if they are very old material, then they will be quite compact as compared to the younger deposits. Okay, so that initial interpretations you can, or I can say the preliminary interpretations you can make based on that also. Okay, then thickness of the unit is also important, and this thickness usually in sedimentary environment you will see that the thickness never remains the same. But in a very small portion where you have opened up the trench, you will be able to identify that the thickness on the hanging wall is different as compared to the foot wall. And this is most commonly seen in normal faulting environment and thrust faulting environment. Normal faulting is that where the block is moving down, and the reverse fault or the thrust fault where the block is moving up. Okay, but in strike slip it is again a bit difficult. We will have that part of discussion later on. Okay, now then coming to the primary structures. Okay, so whatever we have learned till now about the secondary features or primary features, secondary structures or primary structures, everything you need to put here as your understanding. Okay, and then bonding surfaces, that is the contacts. Okay, that what I was emphasizing in the previous lectures, that you have to be very careful putting the bonding surfaces, whether it is related to the depositional process, erosional process, or it is tectonics. Okay, that has to be very carefully marked. Okay, so based on this understanding, we usually prepare our trench logs, okay, what we have I have shown you in the previous lecture, okay, that how we demarcate each and then put it on the graph sheet, okay. And then finally you have to look for the deformational structures, and this will be done based on your shear fabric or deformational fabric of the material you see in the trench, exposed trench. So very carefully you can do that. And as I told that one has now a facility available that you have technique that you can put it on. Now we are having digital cameras, so you can directly import that on your desktop and high resolution photographs, and then you can map those, okay. So this is one example of the trench where each and every information has been marked, okay. The structures, sedimentary structures, secondary structures, contacts between the different litho units, shape of the gravels, okay, and also there is what we call the sorting part, okay. On the eastern portion of the trench, okay, if you see here, this one is the eastern portion, this is the western portion of the trench. We see that there is a quite distinct horizontal stratification in this portion, okay. Whereas just on the other side of the fault line, this dark line is indicating the fault strands, okay. And this is in sort of a normal fault. Well, this block has moved down, okay. So you see a thick deposits, few are showing some sort of a stratification, which you can see here. There's a stratification here, and then you have a sort of a cluvial material, angular material, which has not been transported for a longer distance, okay. So these are the basics of what we learn in the sedimentary geology, okay. Mapping of shear fabric, as I have emphasized in one of the slide in the previous lecture, that also helps you in fixing up your contacts, okay, and differentiating between the whether it is an primary contact or secondary contact. So here you can clearly see this contact here, okay. So this is nothing to do with the primary one, this is all secondary one, okay. And here also, if you see carefully, then you have many such contacts which you can easily pick up and talk about the fault, okay. Because on either side the pattern of sedimentary unit or the structures are different, okay. So here of course you can see this as a micro faulting, what we call, but this is a major fault, okay. Now as we were talking about the shear fabric and very detailed mapping should be done. Now this is the trench log from Himalayas, and we opened up this trench in the foothill zone of Himalayan Kumaon region, okay. Now if we look at what I was emphasizing in the previous lecture, that one has to open the trench covering the both the portions, that is your deformed zone and then you are having undeformed zone, okay. So we put the trench over here like this, okay. And this was your like our Himalayan frontal thrust, okay. So this is your north and this is south, which we mark the Indo-Gangetic plains, okay. This one is Indo-Gangetic. So this is your north and south. And what we saw was like it is mostly common in most of the areas, because you have the deformed zone and then you are opening the undeformed zone. So what we expect is that the deformation will be on this, okay, this part, and then you are expecting that there will be in horizontal undeformed units over here. But apart from that, what is important, which we have marked here, that what I was emphasizing in the previous lecture, is that we have marked and I measured the dip of the fault plane and different strands, and also the dip of your stratigraphic contacts. Okay. So the next one is your, like we have after identifying your contacts, okay, where you have this contact is in your depositional contact. Okay. Further, this also is your depositional contact, and here what we see are all your tectonic one. Okay. So after demarcating or identifying these contacts, okay, and also the amount of dip and everything based on that, okay, and putting all the important information such as the shear fabric, okay, we identify or we decide the locations of sampling. Okay. So this is what we did. Okay. So how many samples from which layer has to be collected. Okay. So each and every layer we collected the sample, but this was been decided after we understand that what are what is the deformation pattern in this. Okay. Other than that, few of the part has been like highlighted here, like shear fabric, elongated pebbles are been aligned with the fall plane. But as I mentioned in the previous lecture also, that now you have a digital platform available where you have digital photographs, you can mosaic it, and then you can have more detailed uh, trench logs. Okay. And then as you move further down, okay, the next part, okay, so you see this, that they are almost becoming horizontal. Okay. The units are almost horizontal. And similar units you also see in the deformation zone. So this is your deformation zone where we were looking at. Okay. And right now what we see is this portion. Again here, after identifying the contacts, and this is undeformed. Okay. There is no deformation in this. Okay. Comparative or respective layers which we came across in the deformation zone or the hanging wall, because this we call this as a hanging wall. Okay. That portion has been compared with the footwall side, okay, and we accordingly we took the samples here also. Okay. There are more techniques which are available. This is from Japan, where you don't need to have wide trenches involved for a couple of days cleaning those trenches and all that, or trench walls which are exposed. This is what they call geoslicer. Okay. So they invented this geoslicer, and this was been invented by Professor Nakata of Hiroshima University. So what he thought of, that why can't we have very quick sections across the fault instead of putting a wide trench. And in this case what they are using is this vibrator here, and this is a sort of a thick steel plate, okay, which has been hammered down into the ground. Once you have the fault trace, okay, that you can do and remove the slice. Okay. And how it comes out, I will show that here. But you need machinery for that, and a lot of course, the cost wise initially it will be expensive, but if you do multiple geoslicing, and you can save the time as well as you can save the money also in this sense. Okay. Further, in some locations you don't have enough space which is available for putting this wide trench. Okay. There you can use this geoslicer. But again, there is limitations to this, because geoslicer will not work in the areas where the sediment succession is full of gravels. Okay. So, you will not be able to penetrate this geoslice. Okay. So, as I told that this is like very almost like 2 meters by 1 meter, and then you insert this into ground by hammering it. So, this is what has been done. Okay. And then after doing this, you cover with this plate, so that you will have a slice which is coming up in this box. Okay. And finally, you will have this type of sections which are available. You can clean it, and even you can peel it, actually, that what we do, and bring back to your lab. So, this was the exercise which was been done and very commonly done in Japan, because they have the softer sediment successions in some locations where it works very precisely. Nevertheless, they also tried and were successful in the area where they had gravels. Okay. But you can see the size of the gravel is not so big, so the large, so they were able to do that. So, this photograph is the made up from, or the mosaic from, 3 geoslices. So, 3 geoslices were been used, and what we see now on this photograph is framed. Okay. It has been kept in lab, or I would say it has been kept in museum. Okay. And you can clearly see the fault which is running here, which goes like this. Okay. And over here also. Okay. So, you can easily interpret or study or restudy or reinterpret, because once the trench is open, after that you need to fill up that trench. Okay. So, you do not have that much of exposure to the sediment succession, but here in this case you can study any time. Okay. And more precisely you can prepare your maps. So, this is one of the best way to reduce the time and put the trenches where you do not have enough space available on site. There is another example of the geoslice which they took, and you can see the faulting very clear over here. Okay. And this also. Okay. This goes here, another one is going here. Okay. Further, in Japan, this is one of the mandatory process where each scientist or the researchers has to do, is that public awareness. So, you need to conduct outreach programs, need to invite the local people and local administration wherever you are opening up the trench, and what are your findings. Okay. And this make people aware that what happens exactly during an earthquake. Okay. So, with this I will stop here. I will continue in the next lecture with a new topic. Thank you so much. Namaskar.